Now let's talk about exponential growth. I could also try to model exponential decay. Exponential growth often happens with populations, often happens with growth in your money in a bank account or some other investment. Exponential decay happens with radioactive decay, for example. It also happens with depreciation in the value of your car. Let's pretend we're thinking about exponential growth, and let's pretend in particular we're thinking about population growth. Let's say P is the population of some group of people or bunnies or something at time T. In both of the examples for today, free fall without air resistance and exponential growth, you can talk about this without talking about differential equations at all, right? You could go, your physics teacher could give you your big four equations and you don't even have to talk about calculus. You could say, hey, this is the height, it matches experiment. That's the velocity, it matches experiment. With population growth, exponential growth, you could just say, okay, I want to use an exponential function, 2 to the t or 3 to the t, or with money, it might be 1.05 to the t, if it's 5% annual growth, for example. Or maybe, because we're talking calculus, maybe we'd want to use base e to the t, e to the 2t, e to the 3t, or maybe e to the 0.1t. Would all be examples of exponential growth base e. So we can talk about this without talking about calculus, and you have in the past, both in Calc 1 and even in pre-calc. So why do we want to talk about this with differential equations? Because it allows us to generalize and deal with more complicated situations. With the free fall, we can talk about what happens when you add air resistance. With exponential growth, we can generalize to non-exponential growth, perhaps. In fact, we even will today. It's called logistic growth. Logistic growth. Well, let's start simple. The key question is to describe this in terms of differential equations is, how do you write the derivative of P with respect to T in terms of what's really its main property? And what do I mean by that? What's the main key property about the derivative of e to the t with respect to t? This is not a trick question. I'm thinking simple here. What is the derivative of e to the t with respect to t? It equals e to the t. In other words, itself. That's probably the most important specialized equation in calculus. And it's also the easiest to remember. What about the derivative of e to the 2t? It's e to the 2t times 2 by the chain rule, 2 times itself. E to the 3t, its derivative is 3 times e to the 3t, 3 times itself. It's always proportional to itself. dp dt is some constant times p, or some constant k bigger than 0. That's how to represent the key property of exponential growth functions in terms of derivatives. The derivative of an exponential growth function is a constant times itself. It's worth writing that out in words. And let me even avoid using the phrase exponential growth. This differential equation is saying that P is a function of T whose derivative with respect to that variable, with respect to T, is always, for all T, equal to a constant times itself, equal to K times itself. the function itself. It's important to understand what differential equations are saying. Can differential equations talk? We pretend they talk. We talk with differential equations. Okay? Really, it's worthwhile to pretend. What is this differential equation saying to me? It's saying P is a function of T, because that's implicit because I'm differentiating P with respect to T. Whose derivative, dp dt, is K times itself. P is itself. P is a function of T, even though you don't see any T's on the right. Why? Because we say so. That's why. We're assuming P is a function of T. This is just like in Calc 1. Remember implicit differentiation in Calc 1? Maybe you had an equation x cubed plus x times y to the 4th power equals blah, blah, blah. It's an equation that's impossible to solve for y as a function of x. Maybe. But we still could assume y is a function of x and differentiate both sides under that assumption. And you'd write dy dx when you differentiate y with respect to x instead of 0, because you assumed y depended on x. Another example is related rates. Maybe you've got a cone filled with water and the water is leaking out through the bottom. The water level is going down. The volume of water is decreasing, and also the radius of the cone of water is decreasing as the water leaks out the bottom. Both the volume V and the radius R of that inverted cone of water depend on T. And you differentiate in related rates problems with respect to time. Even though you don't see T's in the equation, you're assuming they depend on T, because that's what's happening in the application. This is very similar to that. You don't see it in T's there, but it's implicit that P depends on T, either because I say it up here or because the derivative's there, so P must depend on T. We solved the first kind of differential equation. First example, free fall by integrating. Can we integrate here? If we did, wouldn't we get kp squared over 2 plus c? No, don't do that. P is a function of t. Don't integrate with respect to p. We will talk about a method called separation of variables, probably still this week. For sure, well, that's Wednesday. For sure next Monday, maybe on Friday. Where you will do an integral with respect to p in this situation, but it's not right away. That method's probably worth waiting until next Monday. Don't integrate here. I mean, if you were going to integrate, you'd have to, with respect to t, you'd have to replace p with what it depends on t, how it depends on t. But you don't know how it depends on t, at least you're pretending you don't. So what do? In a simple enough situation like this, you just guess the answer. And because we have experience with the exponential growth functions and their derivatives, we know what to guess. Guess an exponential growth function. Leave a little space. Use base e because it's easier to differentiate. Either t? No. I need the derivative to be k times the function. I need e to the kt. Why did I leave a little space? Because I need a constant of integration. Let's not call it a constant of integration. Let's just call it an arbitrary constant. Should I add it? Should I put plus c? Turns out the answer is no. Multiply by c. We should check this, but this is the correct answer, and this is a general solution. E is the special number, 2.71828, blah, blah, blah. It's irrational, but we know from calculus it's special. K, T is the independent variable. K is a specific constant. It's the constant in the differential equation. It must match the K up there. C is an arbitrary constant. It can be anything. Specific constant. It's got to match the K up there. C is an arbitrary constant. It can be anything. We should check that this works. How? Go back up into the differential equation and substitute. Forgot that that wouldn't help, but it makes it a little bit bigger for you. There's the differential equation. Its left-hand side is dp dt. Substitute this function of t. In other words, find its derivative with respect to t. C e to the kt, then by the chain rule times an extra factor of k. That's the chain rule there. But hey, that's p. This is the same as k times p. No matter what t is, for all t, it doesn't matter what t is. Done. That checks it. That means it solves the differential equation, because there's the differential equation there. dp dt is k times p. I have verified that that function works. You might wonder, why not? Why not p equals e to the kt plus c? The reason is because if you check it, it won't work. Why not that? dp dt, if you differentiate this, is k times e to the kt, oops, k times e to the kt plus 0. Derivative of c is 0. In other words, it's k times e to the kt. Does that equal k times the function? K times p. The first part does, but not the second part. I get a plus kc. And if c is not 0, these are not the same function. That's a sideways not equal to there. Not the same function. I mean, they are equal if c is 0, but in general, c is not 0. So that's why not. This function, when c is non-zero, does not have the property that its derivative is always k times itself. Go back to the actual answer. How do we use this? You need an initial condition, like an initial population. If p is c times e to the kt and the initial population is 1,000, that will imply that 1,000 equals c times e to the 0. I'm using function notation there, p of 0, even though you might argue that's a bad thing to do because p is a variable, not a function name. But people do it. Don't worry about it. I did it with the velocity and the height as well. E to the 0 is 1, so this is c. C is 1,000. So in both applications, the c's ended up being the initial values. The initial population here, back over here, the C1 and the C2 were the initial velocity and initial height. Does that always happen? Short answer, no, it doesn't. The c is not always the initial value. So this is the function you would use if the initial population is 1,000. What's k? You'd have to figure it out from some other data. Like maybe you know the population after 1 year. That would help you figure out k. Make sense? You have to use logarithms to solve for k. You've done that kind of thing before. Let's end class by doing a harder example. Logistic growth. And if I'm going to be consistent with the example from the first section, I'm going to pick the following differential equation, which is not the most ideal one to pick, it turns out, but I'll pick it anyway. dp dt is p times 1,000 minus p. What is this differential equation saying to us? It's talking. What is it saying? It's saying, hey, find a function whose derivative with respect to t is always the function times, in parentheses, 1,000 minus the function. No matter what t is. Sounds hard. Yeah, it's hard. Let's use Mathematica to figure it out. D-solve is one way to do it, but I prefer using D-solve value. This is worth writing down. It might be something I put on the final exam. Capital D, capital S, capital V. First thing to do is to type in the differential equation. Do you type it just like I wrote it by hand? No. For one thing, you don't use Leibniz notation. You do not write dp dt like that. Don't do that. Write p prime of t. P prime of t. You also use 2 equal signs instead of 1 equal sign. Make sure you don't make the mistake of putting 1 equal sign because it messes things up. On the right side, you put what you see, p times 1,000 minus p, but you do need to tell Mathematica that p depends on t by doing it like this. So double p prime, not dp dt. Use the square brackets for variable inputs like usual. Use double equal signs. And yeah, make sure you put the square brackets t for the p's on the right side. Can we write the t's by hand? You could. It's traditional not to. There are also good pedagogical reasons not to, that we'll talk about more on Friday and next Monday. So by hand, we do not put the t's explicitly on the right. Then put a comma. Then put the function you're trying to solve for, p of t, another comma, and then the independent variable, close bracket. Enter it. Mathematica is saying effectively that this is the general solution. Now, that's not the most typical way to write a general solution. I, in fact, am going to write it by hand differently than that. What I'm effectively going to do is I am going to treat this e to the 1,000 c1 as just a plain old c. That's one change I'm going to make. Another change I'm going to make, and this is traditional, is I'm going to divide the top and the bottom of this fraction by e to the 1,000t. It's a really big power for the exponential function. That's why it's maybe not ideal to use 1,000 there. I should have used a smaller number, but not a real big deal. I'm going to divide the top and the bottom of this fraction by e to the 1,000t. If I do it to both the top and the bottom, it doesn't change the function. So it's going to cancel the e to the 1,000t on top, leaving me with just 1,000. On the bottom, it's going to cancel here, leaving me with a 1. And I'm going to divide C by that. I'll get C e to the negative 1000t. Okay, I'm going to write the general solution like that. Okay, in 3 minutes, I want to confirm that this solves the differential equation. Okay, I'm not telling you how Mathematica got it. I'm just saying check that it solves the differential equation. We got to take the left-hand side of the differential equation. LHS stands for left-hand side. It's dp dt. I got to find the derivative of this. It's a quotient. Use the quotient rule. I guess I heard from the first class that Alk did not do it in the way that I teach people to do it. Low d high minus high d low over the square of what's below. If you're in Alk's class, you probably did not learn that. But I'm telling you it's a nice way to learn it. Low d high, the derivative of the top. D means derivative, which is 0. That's nice. Low d high minus high. D low means the derivative of the low function. The chaining rule gives an extra factor of negative 1000 over the square of what's below. Low d high minus high d low over the square of what's below. And this simplifies a little bit to 1000 squared, which is 1,000,000. C e to the negative 1000 t over 1 plus c e to the negative 1000 t quantity squared. What about the right-hand side of the differential equation? RHS means right-hand side. P times 1000 minus P. I've got to take this function and substitute it in place of P in 2 spots. At the beginning, and then do 1000 minus the function. How is this possibly going to simplify to the same thing? Amazingly, it does. Get a common denominator in here. This 1000 is the same as, if you get that denominator, 1000 plus 1000 c e to the negative 1000 t divided by 1 plus c e to the negative 1000 t. And then once you've got that new fraction with that new common denominator, add the numerators, and you got a minus sign there. So the 1000 there, so it cancels with the 1000 there. And you're left with, after cancellation, this thing inside the parentheses. When you multiply it by this, you get the same thing. You get 1000 squared c e to the negative 1000 t divided by 1 plus c e to the negative 1000 t quantity squared. We have a match. We are very, very happy. Match. Happy face. Praise the Lord. PTL. That means it solves the differential equation. And any other function that cannot be put in the form that I wrote down would not work. You could try it. Its derivative would not be itself times 1000 minus itself. Okay? Not telling you how Mathematica got it. We're just trusting it. You should be able to check solutions like this, though. See you on Friday.